All right. So we talked a little bit in the previous class period about writing out electron configuration. And remember, we said that electron configuration, it just shows where all the electrons are at. It's how we describe the location, the position, and the energy of the electrons. And it's very repetitive. And before, in the last class period, we used this chart right here, to show us which orbitals fill with electrons first. And we said that first the 1s orbital fills, and then we go to the 2s orbital, and then we keep going, and the next one that fills is 2p, and then 3s, and then we go over to 3p and 4s, and then we go to 3d, and then 4p, and then 5s, and we have this sort of pattern, okay? So what is the final, we wrote potassium's electron configuration down here. What is the final orbital that filled in potassium's electron configuration? What is the final orbital, the last orbital that we put electrons in? And go ahead and type your answer into the chat. What is the last orbital that we put electrons in? And give me both the energy level and the type, the subshell. So both the energy level and the subshell. Okay, all right, I'm seeing a lot of us put the right answer. So the final orbitals that filled were the 4s orbital. And we only ended up putting one electron in that 4s orbital, but that was the last orbital that was filled. Okay, so hopefully this sounds familiar. You've listened last week, and now we're just going to talk about a little bit about a few other things. So we can use that chart to write electron configuration, but you don't have to have that chart because the periodic table actually mimics the order in which electrons fill into orbitals. So if we read the periodic table from left to right, so we start on the left and we go to the right, we can find the order that the orbitals fill just by looking at the periodic table and kind of knowing how it's structured. So all these elements that I have colored in red, they're a part of a periodic table called the S block. And so the final electron that goes into the electron configuration for all these elements will go into an S-type orbital. So that's what the S block means. And helium is over in the S block, even though it's out of place. It actually fits in right over here. We just put it over in group 18 because it's a noble gas, so it has 8 valence electrons, so we put it over here. But in reality, its electron configuration belongs over in group 2 of the periodic table. So the red's the S block, and then we go over here into the green, and we have the P block. And then in the middle here, our transition metals is called the D block. And that may sound familiar because when you colored your periodic table, I said it referred to the D block elements, the D block elements. So these are the D block elements here in the middle. And then last but not least is the F block. And we said the F block actually fits up here in row 6 and 7, but it's actually 4 and 5F down here. And so as we write out electron configuration, we don't need to use that crisscrossy chart. We can actually use the periodic table. And so to fill in our notes, we can say that the structure of the periodic table mimics the filling of the subshells with electrons. The period, or row, corresponds to the energy level of the valence shell of electrons. And then the group, or column, which these are vocabulary words we've already talked about, the group or column corresponds to the extent that the subshells are filled. And then more importantly, the elements with the same valence shell configuration, so meaning that they're in the same group, valence shell configurations, they share similar properties. So what that means for us is this is a super important thing. All these elements in group 1 are going to end, their electron configuration will end with S1. All the elements in group 2, their electron configuration will end with S2. And then over here we get into the p block, so all the electron configurations in group 13 will end with p1, and so on, and we can keep going. So they share similar properties if they're in the same group because they have the same valence shell configuration, meaning that they end with the same subshell and number of electrons in that subshell. And so let's put this into practice a little bit because this may seem a little foreign until we actually do this. So let's put this into practice. Let's write the electron configuration for oxygen. So oxygen is right here on the periodic table. So let's write the electron configuration for oxygen using the periodic table. And this isn't in your notes, but you can just add it in, or you can just watch, that's fine too. So if we read the periodic table, starting up at the top, we're in row number 1, and we're in the S block of the periodic table because it's red. So this first element would be 1s1, and then the second one would be 1s2. But we know that for both of these pieces, we're going to combine them together in our electron configuration. So the first piece would be 1s2. Then we've finished reading our first row from left to right. So we're going to go down to the second row of the periodic table. Now we're in row 2, so our electron configuration will start with a 2. And we're still in the S block, so we'll start with 2s. And we know that we're going to go both elements across the S block. So we're going to fit 2 electrons into that 2s orbital. And so I could label the boxes here with 2s1 and 2s2, but we know that when we write our configuration, we're going to combine those two things and just write the 2s2 part, okay? If we keep reading across, we're still in the second row of the periodic table, but now we're in the p block over here, so we're no longer in 2s, we're in 2p, so that's telling us that our next set of electrons will go in the 2p orbital. And so we have 2p1, and then 2p2, and 2p3. And oxygen is the fourth one over, so it's 2p4 that our electron configuration for oxygen will end in. So to summarize all this, because we don't want to write all of these different letters and numbers out, we're going to combine the 1s orbitals and write 1s2. So our first piece of our oxygen electron configuration will be 1s2. We're just saying the number of electrons. So oxygen has 8 electrons, so we're going to fill up that 1s orbital with 2 electrons. So instead of writing 1s1, 1s2, 2s1, 2s2, we just combine, if we fill that orbital, we combine it into the last piece. Nope, because the s orbitals can hold a max of 2 electrons, just like before. Max out at 2 electrons. So 1s2, and then we go down to our next row and we write our 2s2. And then this next piece is going to be 2p4 is the highest we get, 2p4. So there's our electron configuration for oxygen. And if we go and we write out our chart that we've been using, whoops, this should be 2s2, 3s2, and then 2p6, 3p6. I can draw this chart out. I'm just going to draw a little bit of the chart, because we don't need the whole thing. So we wrote 1s2, and then we did 2s2, and then we went over into the 2p orbital. So our electron configuration, we're following this chart exactly just by reading the periodic table from left to right. Does anybody have questions on that? Okay, so let's do potassium's electron configuration together. So for potassium, I'm going to go ahead and I'm going to just kind of clear this piece out a little bit because we're not ending with 2p4. we're going to keep going. Okay, so for potassium, let's just go through and say the electron configuration out loud first, and then we'll write it out. So potassium's right here in the periodic table. It's element number 19. So our electron configuration, we're starting with row 1, and then we're starting in the S block. So we're going to write 1s2, because we're going to go all the way across that S block. Then down to the second row, 2s2, because we go all the way across the S block again. Then 2p, and there's 6 total electrons that can go in that 2p set of orbitals. So we'll write 2p6. Then we'll go down to row 3 and write 3s2. Then 3p6. And then our electron configuration for potassium will end with 4s. And since potassium's the first one, we only put 1 electron in that s orbital. So it will end with 4s1. So just to recap, we'll write 1s2, then 2s2, then 2p6, 3s2, 3p6, 4s1 is where we'll end. So let's go ahead and write all that out. So all we're doing here is writing everything out until we get to potassium. So we'll start with 1s2. Let's write that down. 1s2. Then 2s2, 2p6, okay, then we go down to row 3, 3s2, then 3p, and we're going all the way across, so 6, 3p6, and then 4s, and we're only 1 into the s block, so we're going to end with 4s1. Okay, anybody have questions on that? So if we look at our chart here, we can see that following the periodic table gives us the exact same thing as following our chart. If we followed our chart, we would have gotten 1s2, then 2s2, 2p6, then 3s2, 3p6, and then we would end with 4s, but we only have 1 electron, so instead of writing 4s2, we just have 4s1. Does anybody have questions on that? You can put your questions in the chat, or you can say them out loud. Okay, awesome. So let's talk about noble, or actually, before we go to noble gas notation, let's do one more example, just to make sure we are all on the same page. So write the electron configuration for iron, which is chemical symbol Fe, using your periodic table. So write the electron configuration for iron, which is chemical symbol Fe. Iron is right here, number 26. Okay, and try to use your periodic table and not your crisscross chart here. So just kind of to start this out, we're going to start by writing 1s2, then we'll go down to 2s2, 2p6, 3s2, 3p6, 4s2, and then notice after 4s2, the next orbital that fills is in the d block, but it's not 4d, it's actually 3d. So when we go into the d block, we have to remember that the number of that set of d orbitals is 1 less than the set of s orbitals. So this is actually 3d, and then 4d, and then 5d, and then 6d. So after 4s2, then we do 3d, and then we're 1, 2, 3, 4, 5, 6 into the d block. So it'll be 3d6 will be what iron's electron configuration will end with. So let's go ahead and write that out. So 1s2, then 2s2. So I'll start by writing that. 1s2, 2s2, 2p6, 3s2, 3p6, then we go down to 4s2, and then 3d, and then we said iron is 6 in. So 3d6, and just to double check, it's 1, 2, 3, 4, 5, 6 over. So yes, it is ending in 3d6. Does anyone have questions on that? Okie dokie. We're looking good here. Okay, so let's talk about this idea of noble gas notation. As you might have noticed, writing out electron configuration is a pretty long-winded process. And so scientists wanted a way to show all the electron configuration and where the electrons are and what energy levels they're in without having to do quite so much writing. So noble gas notation is a shorthand way of showing electron configuration. And we'll fill in the notes in just a second, but we're going to do an example of this first. So, for instance, for iron, iron's electron configuration is pretty long, so we can shorten it. Iron's number 26 on the periodic table, but we decided that we can shorten it by using the previous noble gas. And remember, the noble gases are in group 18 of the periodic table. So if we wanted to shorten iron's electron configuration, we can find the noble gas that comes before it and write that part in brackets to show that the electron configuration for iron is the same as argon up until that point. So we can say that the first 18 electrons in iron's electron configuration, we can summarize the first 18 electrons, so all the way up until 3p6. All of this right here can be summarized to say, you know what? All these electrons are the exact same configuration as argon. So what we do is we put the noble gas chemical symbol in brackets, just like that, and say, okay, all these electrons right here, all of these electrons, the first 18 electrons, they're the exact same electron configuration as argon. And then all we do is write the part of the configuration that comes after that noble gas. So after argon, we have 4s2, and then we have 3d6. So we can just write that remaining piece and shorten this a whole lot more. So 4s2, and then 3d6. And so this is what we call the noble gas notation. And notice it's a lot shorter than our full electron configuration. These first 18 electrons, they're the exact same configuration as argon, so we can summarize by saying, okay, same as argon, plus 4s2, plus 3d6. Does anybody have questions about that? All right, let's fill in our notes. So this first blank, or actually the only blank, is just noble gas notation. And so we can shorten potassium's electron configuration, which we've written out before. We wrote out potassium's electron configuration here. We can shorten potassium's electron configuration by saying, okay, potassium's first 18 electrons are the exact same thing as argon. So we're going to summarize those first 18 electrons just by putting AR in brackets. And then after argon, the piece that's left is the 4s1 part. So that shortens potassium's electron configuration a whole lot. These first 18 electrons can be summarized to say they are the exact same thing as argon, and then the part that's left is the 4s1. So we just write that. So that's where we got the shorthand electron configuration of argon in brackets and then 4s1. Anyone have questions there? Okay, let's do a few more examples just to kind of get our feet wet here. Let's write the noble gas notation for cesium. Cesium, number 55. And no, you do not have to write the full electron configuration. We're just writing the noble gas notation for cesium. So if we wanted to write that noble gas notation, what noble gas comes before cesium? And remember, the noble gases are over here in group 18. Which noble gas comes before cesium? Put your answer in the chat. What noble gas comes before cesium? Make sure you're doing your chemical symboling correct. So one letter should be uppercase, one should be lowercase. What noble gas comes before cesium? Okay, so I'm seeing a few answers. The noble gas that comes before cesium, so before number 55, is xenon. So we can summarize those first 55 electrons by saying, you know what, they are the exact same thing as xenon. And then we're just going to write the part of the configuration that comes after xenon, which is 6s, because we're in the s block, 6s1. Okay, any questions there? All right, let's do another one. Let's write the noble gas notation for molybdenum, MO. Let's write the noble gas notation for molybdenum, MO. I'm going to erase some of this. MO for MO. So molybdenum is number 42 right here. What's the noble gas that comes before molybdenum? Put your answer in the chat. What should our noble gas notation start with? What symbol should go in those brackets? Find the noble gas that comes before molybdenum. I have seen a lot of perfect answers here, so if we go back before molybdenum, we go back, we jump up to row 4, and the noble gas that comes before molybdenum is right here, Kr, krypton. So in our brackets, we're going to put Kr. Okay? So after krypton, we need to do the rest of the configuration that comes after krypton. So after that, we get 5s2, and then we have 4d, and molybdenum is the fourth one over, so 4d4. 5s2, 4d4. Okay, questions there? Anybody have questions? All right, let's do one more example before we break off. Let's do the noble gas notation for polonium, number 84, PO. Let's do the noble gas notation, the shorthand electron configuration for PO. All right, so first of all, which noble gas comes before PO? So go back on your periodic table, find the noble gas that comes before PO, type your answer in the chat. What noble gas comes before PO? What noble gas are we going to put in our brackets? What noble gas are we going to put in our brackets? All right, so the noble gas that's going in our brackets is indeed xenon, which is number 54, so Xe. And then we are just going to write the part of our configuration that comes after xenon. So after xenon, after number 54, the next electrons go in the 6s orbital, so 6s2. 5d, and we're going all the way across, so that's 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way across. So 6s2, 5d10, and then 6p, and polonium is the fourth one over, so 6p4. So let's write out that last part. 6s2, 5d10, and then 6p4. Okay. Questions there? Are there any pieces in the notes that we did not fill in? Anyone have a question or blank that they missed? All right, last but not least, we're going to practice writing the full electron configuration and then drawing a Bohr model to show where the electrons are, to show what energy level the electrons are in. So we're going to do this for bromine. So start out by writing your electron configuration for bromine out. Use your periodic table and write the full electron configuration for bromine. And while you do it, I'm going to write it up here. and then you can check against mine. So if we use our periodic table, we're starting with 1s2, then 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d10. And then after that, we have 4p5. So there's our full electron configuration for bromine. So if we wanted to draw this as a Bohr model, we're going to put a Br in the middle. And then the first thing we need to know is how many total energy levels do we have? So looking at this electron configuration, how many energy levels do we have here? How many, what is the largest coefficient that you see out front of one of our electron configurations? So I see energy level 1, I see some energy level 2, I see some energy level 3, and I see some energy level 4. So I see 4 total energy levels. So I'm going to go ahead and draw 4 rings in my Bohr model. And my picture may not be so great because I'm not the best artist here. So 3 and 4. 4 rings on our Bohr model. So now we just need to figure out how many electrons go in each of those rings. So when I do this, I like to start with the valence shell of electrons. So my outermost shell is energy level number 4. So I'm going to pick all the pieces of my electron configuration that have energy level number 4, and then I'm going to add the number of electrons in those together. So I see 4s2 and 4p5, and I have 2 electrons in my 4s orbital, and then 5 electrons in my 4p orbitals. So 2 plus 5 gives me a total of 7 electrons in that valence shell. So I'm going to go ahead and put a 7. I'm not going to draw dots for this just because it takes so long. So just put numbers when you draw Bohr models here. Just put a number on each energy level. So this has 7 electrons. So I'll put 7 E minus. 7 electrons. Any questions there? Okay, let's go down an energy level to energy level number 3. Now I see that I have 3s, 3p, and 3d. So I need to add all these electrons together. So I have 2 plus 6 plus 10. So that gives me a total, 2 plus 6 plus 10. So that gives me a total of 18 electrons in that third energy level. So instead of writing 18 dots, I'm just going to put the number 18 E minus. 18 electrons in that third energy level. Going down to energy level 2, I see that I have 2 and 2. So I have an S and a P, so I have 2 plus 6 electrons in that second energy level. 2 plus 6 gives me 8 electrons. So in energy level 2, I have 8 electrons, 8 E minus. And then last but not least, in energy level 1, all I have is that s orbital, so I just have 2 electrons in that first energy level, 2 E minus.